we're going to try problem 22 here, car stopping, distance, and friction. Okay, read the problem. Think about it for a moment. All right, now the key things here are this. The car starts at 97 kilometers. It stops after 48 meters. We're looking for a coefficient of friction and between the tires and the road, and they say that it's skidding. And that means what we care about is kinetic friction. So we're going to use this idea of kinetic friction, this initial speed of 97, and the fact that it travels 48 meters to try to do this problem. Okay, so we're going to come down here. This is problem number 22, and we're going to draw a little picture, and we're going to imagine this car is able to skid for 48 meters. And we're also going to remember that there are forces on this car. There's the weight of the car, mg, which we don't know because they don't tell us anything about the weight, but we do know that the normal force must balance the weight because the car's not accelerating up or down. And that when they slam on the brakes, we get a frictional force, and that frictional force of that kinetic friction is equal to the coefficient of kinetic friction times that normal force. And this is pretty cool because it tells us that the frictional force is mu k times the normal force, but the normal force is mg. And the only force acting in the horizontal direction, so if I now say F net equals ma, the only force acting in the horizontal direction is the frictional force. See, there's only one arrow here that's horizontal. So all forces added together are the same thing as just the frictional force. So F net is mu k times mg, and that equals ma, and that tells us that if I wanted to know what's this coefficient of kinetic friction, well, the m's very conveniently cancel. It would be the same as the acceleration divided by little g. And they want us to figure this thing out, and I already know little g is 10 meters per second squared, so that means I'd just like to know what this a was. How can I figure out that a? So I'm hoping that this 48 meters is going to help me get that average acceleration. Now, here's a case where what I want is an acceleration, and I know a distance. So I want this acceleration, and I know that it's a distance that I've traveled that's going to help me figure out that acceleration. And here it's very sort of a quick, lazy thing to do in a way, is to take a look at a set of kinematics equations. And what we have up here, if I just type kinematics into Google and hit images, I get lots of different versions of these kinematics equations. Now, you really should be able to derive all of these, but if you look up at the image here that's got 1, 2, 3, and 4, I'd like you to look at number 4 for a minute. It says v squared equals v0 squared plus 2a delta x. We're going to explore whether this one is useful or not. So I'm going to use what I typically have been using. So I'm going to say v squared is v, I've been using vi, so vi squared plus 2a. And I'm just going to use d for the distance instead of delta x. And the reason I like this particular equation is that I know the d is the 48 meters. This is going to be 48 meters. And I know this vi from the problem is 97 kilometers per hour. And so that means I know those two things. I also know that this is when I stop. So this is going to equal 0. And what that shows me then is I've got one equation with just one unknown. The only thing that's not known here is a. And that's great, because I've got one equation I can solve for a. In fact, if I solve for this in terms of just the letters, I'm going to have 0 equals vi squared plus 2a times d. And I can use a little algebra to show that this must be a equals vi squared over 2d. And that's cool, because I can even stick in those values now. I can stick in the 97 kilometers per hour, square it, right, and divide by 2 times 45 meters. Then I can even take that and combine it with this over here, and I'll be able to solve for that mu k. So if I really wanted to go all the way to the end here, I could say mu k equals a over g, and so it's going to be, in fact, if I keep the letters, I'm going to get 2d, right, over little g, and that's going to be the same as vi squared over 2g times d. And now I can go ahead and stick in again all of these numbers if I want to. I've got 97 kilometers per hour squared over 2 times 10 meters per second squared times 45 meters. And I can tell when I just look at the units, like meters and meters, those are going to be able to cancel those 2 kilometers, a kilometer squared at some point. And these seconds squared is going to go to the numerator, and that's going to somehow be able to cancel that with those hours. So if I really want to kind of keep this up, I've got 97. No, I've got kilometers is 1,000 meters. So I've got 1,000 meters here, right? And per hour means, an hour is 3,600 seconds, right? Like that. This whole thing is going to be squared. And I'm going to have to divide all of this by, I guess, 20 times 45, right? 2 times 45 is 90. 90 times 10 is be 900. I think I'm going to have 900, and I'll have meters squared per second squared. And now I can see that the meters per second squared here and the meters over seconds squared here are going to cancel. And so I'm going to finally come up with some result that looks like it might make sense. I'll have 97 squared, so 97 times 97. I'll have 1,000 times 1,000, right? So that's 1,000 times 1,000. The whole thing is going to be over 3,600, and then there's also going to be this 900 down here. And if I just wanted to do a quick estimate, you guys can multiply all of this out if you want to, but if I wanted to try to do a quick estimate, I would take this 1,000, I would change that to, say, 0.9 maybe. Here I have 3,600, I can change that to 3.6 and then get rid of the other 1,000. And hang on just a minute, I'm a little bothered by the numbers I see. Oops, I forgot the 3,600. There's another 3,600. The whole thing was squared, wasn't it? Okay, that's going to get me a number that looks like it's a little bit like that'll make a little more sense to me. So at this point, this is sort of silly. You do this on your calculator. 97 times 97 over 3,600 times 3.6 times 0.9, and of course you didn't have to do all of these steps. But we should get a number. Let's see, what are we going to get? 97 times 97 is about 100 times 100. 100 times 100 is about is 10,000. 10,000 over, let's see, 1,000 over 3.6 and 3.6 and 0.9. Let's see, 10,000. Well, hang on. Okay, well, my apologies. I see after looking at this more carefully that for whatever reason, somehow I decided to call this 45 instead of 48. It's 48 meters, right? So then this would not have been 900. This would have been closer to 1,000. And you guys can, again, do all the, do this correctly if you want. 1,000 will cancel with one of those thousands. And I'm going to get a value of maybe 3 over 3.6 roughly. Or, I don't know, I'll probably get somewhere around 0.7 or something like that, or 0.75. Okay, sorry for the sloppiness there, but you can double check and see if you get a number anywhere roughly close to that, and then review the concepts, which are much more important than those calculations.